Alrighty, so let's see some quick reminder. Your assignment number 1, I hope everybody made it to the deadline, I hope, right? The solution is going to be released very soon, either later this afternoon or early tomorrow for sure. So there will be source code about a solution. You can go over them and reach out to me if you got any doubts about the solution I give to you. Just one way to solve the problem. May not be the only way, right? So if you want to discuss, be my guest. Just feel free to drop by. And also there will be some like a tutorial video just walk you through some of the solution. If you find them useful, you can also look at them, okay? And then again, guys, split array harder. So far, some of your fellow students drop by and then show me their solution. I'm actually quite impressed about they actually did. But give it a try. And then if you really get stuck about this problem here, just drop by. And then we can discuss your idea. It's actually quite a useful exercise for you about your upcoming programming test. And speaking of your programming test, don't worry, I will reach out to you about some example questions and some guidance pretty soon. Okay. And office hour and also TA contact, just the same, always there, right? Just use them when you find a need. Any question about the course in general? Alrighty, let's now talk about some recap very quickly, and then we'll move on. So last time we basically still kind of focus on the mathematical properties for big O, which is important because after basically we already finished all the like a big O related math on last Thursday. So today, starting from today, we're going to see more about linking math into coding. You're going to see some interesting or tricky example to really consider. We'll see. It's actually quite fun. Okay, but let's do a quick recap about what properties we actually went over last time. So we did some visual summary about the big O formal definition, right? You just got to remember you got a reference function manipulated by some multiplicative. You got some reference function got manipulated by some multiplicative constant c by changing its slope, and also you got a function you want to upper bound, which is a running time function, right? So we have seen this definition for many times from many different angles. You really want to make sure you understand that thoroughly before you write a test or an exam. Excuse me. And then we also got some alternative definition of the big O using what you guys learned from 1019, practical logic. Just also try to understand that it does give you a little bit more insight into what's really being proved. Right? You got to choose the C and N0 first to be a witness. And we did this proof about some strategy over here. You can simply choose some fixed C, which will be the summation of the absolute values, and also N0 always be 1. I would say most of the cases, as we have seen most of the example we did, N0, yes, it will be 1. But when log is involved, N0 may not be 1. So you always got to verify, right? So that's the example we did. And please go over the proof and relearn some insight from there. Simple math, but it does give you good insight. And we did this example here by applying the strategy, and don't forget, always verify whether N0 equals 1 is where the upper bound effects will start showing. If it doesn't, you may want to try another value for N0. And we spoke about some properties of big O. So within a particular big O family, let's say the power here is 1. That means all the functions that will grow no faster than power 1 is going to be included in the family, right? You can look into the lecture from last time to see the discussion. But it's very important to link individual family to the diagram over here, right? That's something I'll let you study. And also you can see n squared family here contains the family for n, right? That's also something we observed. It's also true for other similar scenarios. And we spoke about the subset relation over here, right? So you want to make sure you understand what's proper subset relation. You want to really understand what proper subset really means, right? So if I say big O of n is a proper subset of big O of n squared, that means I can find at least one function there that belongs to n squared. But that function there cannot be upper bounded by the strictly smaller family over here, right? So you got to remember that insight, right? And we might have to revisit this proper subset for a few more occasions in the course. It's a very useful mathematical concept, simple but very useful and practical for us to understand what's going on. And that one there, just another example here, just to show you, for example, 3n belongs to this family here, but this one cannot be upper bounded by the strictly smaller family, right? I kind of spoke about how you can draw the diagram and somehow show almost like a proof to see it can never happen, right? You want to really look into this insight over here. If I ask you maybe in the exam or in the written test, if I simply change the power here slightly, you should still be able to do it, right? Try different variants, try different variants of the problem, and then convince yourself. Right, so that's the final diagram we kind of summarized, right? You can see we got increasing power of family for the big O, right? And it's a proper subset relation throughout. And you should be able to also find some example, let's say that belongs to this family here, but does not belong to this family, and etc. Okay. And we also talk about whenever you want to give the asymptotic upper bound, being correct, of course, must be the case. But you also want to be accurate as well, right? So for example, let's say if you talk about 7n minus 2, it does belong to the n to the power of 1 family, but it also belongs to n to the power of 3 family. So it would be correct if you say 7n minus 2 is a member of this, and this. So all these 4 are correct, but you are supposed to choose the most accurate one and present it. And we talk about if you actually didn't choose the most accurate one, but just correct one, you might have some misleading consequence, right? That's something you can also go into detail from last lecture, right? I'm not going to repeat here. And then finally, so you can see whenever you want to present a big O, in the intermediate step, it's okay to sketch the work. I also do that to kind of show you the intermediate work. But I would say the final answer you want to present, you should never ever include any multiplicative constant or any lower term. You should be just a single term, right, without those. All right, so we did, okay, sorry, not yet. So we did a few examples about the given the function and decide a big O, right? You can go over them. And also got some exercise for you. Go over them and then try to see what the answer is, if you can get the answer right. And this example here is the only one that we did where n0 equals 1 is not the case by following the proven strategy. So you should really see why. We kind of show that it cannot be verified. So what you should do instead is to try, rather than 1, maybe try 2. If 2 doesn't work, try 3, and etc. Usually it wouldn't take long for you to find out exactly what should be the appropriate n0 for the upper bound effects. All right, a few exercises. All right, so the last 2 examples we did last time was really to start applying the big O knowledge into coding. Right, we did 2 very simple examples. When you are given a piece of code like this, now the task is not really to count the precise number of primitive operations. We just want to somehow approximate the running time and decide the asymptotic upper bound. So it's really to approximate. If you're given the task about counting precisely the number of primitive operations, it will be another story. I'll give you guys a little bit more example later or exercise to try. But for now, let's focus on approximating. Right, so for all these, we argue that each one of them will just be like a constant number of primitive operation. It does not depend on any like input array size. So all of them will just be 1, right? So big O of 1, easy. And the second one we did, if you remember find max, where we calculated precisely is 7n minus 2. But for now, we don't really need to calculate precisely. So if you just go line by line over here, you just got to watch out over here for the loop. Since we're going to go from 1 all the way until somewhere very close to n. So we know that asymptotically, the number of iterations is going to be very close to n, right? So we can just approximate like that, right? And what we get is big O of n, right? Right, so that's a recap from last time. Do you guys have any questions? All right, so today we're going to go over with more examples about asymptotic upper bounds on the Java code. And then we'll move on to a new lecture, right? So I got about 2 or 3 examples. 2 of them are tricky, which is good. So we're going to look at them. All right, the first one to look at would be on slide 34. All right, and I'm going to look at, let's look at it here. All right, slide, okay, again, it's, let me see, slide 34, okay, in case you're looking at the slides. All right, so this will be the piece of code where we want to decide the asymptotic upper bound. All right. If I just want to take a guess, maybe later, I might just look at the loops. I got double nested loop. 1 here and 1 is inside. It's kind of nested. And somehow I got 2 loop counter I and J. And also each one of them will be up to n, right? Later on, you might have very good intuition about this should be maybe n squared, maybe, right? Maybe that's what will be your guess. It's a good guess, by the way. It's the answer. I can tell you right away. But what's going to be important right now is for us to derive that systematically. We don't need to calculate precisely the number of primitive operations, but we still want to show some rigorous process for deriving it. Because there will be a different loop pattern that we don't necessarily will always get n squared. Even though we'll get n squared, I want to see how you actually analyze the loop counter pattern to see how you derive that. You don't want to just guess, right? That's not acceptable later. All right, let's now take a look. And to really analyze the running time, I don't even need to understand the logic of the code. I just need to look at the structure of the Java code. That's it. Understanding the logic of how the code works is not a necessity for deriving asymptotic upper bound, right? Keep that point in mind. So let's say during the test or exam, if I give you a piece of code, you don't really have to waste time understanding how it works first, unless I can ask you to trace it, right? It will be a different story. All right, let's now take a look. I want to maybe make some annotation just to show to you. Of course, you got to focus on, there's a double nested loop over here, right? First of all, over here. So I'm just going to box them over here, right? So that's the nested loop that we have to watch out for. And then you may want to look at two different blocks over here. Block number 1. If you look at line number 4, line number 5, and also line number 6, right? So these 3 lines are the body of the inner loop, first of all, right? What does that mean? That means this block of code is going to be executed for every combination of I and j, because this is a nested loop. So every time if there's some combination of I, for example, 0, 0, 0, 1, 0, 2, etc., for each combination, we have to execute this block of code once, right? That's the very first insight you have to realize. All right, let me write it down here. So think about this part here. So let me call this one here. I'll just call it phase 1, okay? P1. Let me call this P1. So P1 gets executed for each combination of the 2 loop counter. Let me say I and j. So we're going to consider how many possible ways are there for I and j. We're going to enumerate them. So this will be the important lesson to learn, to get from this kind of question here. But I'll get there, okay? Another block of code, which would be a little bit easier, would be here. So if you look at this part here, I++, right? That one there is a little bit different, right? You can see here, I++ only gets to be executed for every value of I. For j here, it doesn't really matter, right? You can think about this part over here is going to be executed, and then this part here will be done, and then you get to execute this. Okay, something like that, right? So by the way, so the brackets over here may help you about how things should be understood. You can look at that, right? I'm just telling you the facts pretty quickly. All right, so now I'm going to say P2, okay? Once we understand these 2 important parts, to understand they will not be executed the same amount of time. That's the most important thing to observe. So P2 gets executed for each value of I. Right? So if we know how many iterations there are for the outer loop, then we'll know how many times this I++ will be executed. All right? And before we actually talk about, for example, how many combinations I and j will be, let's speak about individual block first. So let me highlight this as blue. Okay, this one is blue here, right? So they're different. What would be, well, since we know for every combination of I and j, we're going to execute this block of code. So each time, what will be the number of primitive operation for this block of code to be executed? What's the approximation for this block here? Somehow we got primitive, return, also primitive. Also assignments, also primitive, right? All primitive. So I can safely say, for this particular part here, itself, it's big O of 1. If we are going to execute this block n times, it's going to be n times 1. If we're going to execute this block n squared time, then the running time will be n squared, right? Etc. So that's why I want to figure out for each execution how much time it's going to take relatively, right, for this block. And then similarly, if you look at P2 over here, I++, again, you don't need to know the precise number. That one should be just big O of also 1, right? And you also see some return false. That will be outside the loop. That's something we're going to see later. Okay. Alrighty, so let's now focus on the loop pattern here. Okay, so this example here just gives you some introduction about what I really meant by analyzing the loop counter pattern. Okay, so I'm going to write it down here. So what we're going to do is we're going to look at the header over here and analyze right away. And by the way, so hopefully today I can get to some sorting algorithm. If I cannot, definitely Thursday. Once you see the Java code for the implementation for sorting algorithm, this will be something you have to do as well. Okay, we'll see later. So I want to look at a pattern of loop counters. That's what I'm going to look at. All right, of course, here I got I and J, right? So let's talk about I and J. And let me use blue for I. So let's say I'm actually going to use blue. And for J, I'm going to use purple, right? So we got two different variables to keep track, right? Let's start with I, because I is the outer one. What would be the possible values for I? Let me ask this way. How many possible values are there for I? How many? How many? Okay, n possible ways, right? Because we got from 0 all the way to n minus 1, right? It's kind of similar to what we did earlier about find max, right? So what I'm going to do is the first dimension. For the value of I, I'm going to say we got 0, we got 1, we got 2, all the way to the final one is going to be n minus 1, which is still going to trigger some loop iteration, right? Once I gets to n, this Boolean condition will be false. We don't have any more iteration, so we don't consider that case. That's one just constant. We can ignore that. All right, so this part over here will be, so we want to, first of all, we can draw some mini conclusion here. The outer loop runs how many iterations, right? Let me give you guys some useful formula. You might know that already. Let me put it here. All right. You guys learned about interval, right? Maybe back in the calculus class. If I say I got some closed interval, I got maybe A here, I got B here, right? Starting from A, ending with B inclusively. All right? How many numbers are there in this interval? What's the formula, guys? B minus A? Plus 1. All right. The number of integers, let's say, normally we just consider it integers, in this closed, this will be very handy, is B minus A plus 1. For example, if I got, let's say, 0 to, let's say, n minus 1, what would that be? Basically, n minus 1 minus 0 plus 1. That will give me n. Right? If you want some concrete value, for example, I want to go from 2 to 99. Right? How many numbers are there? Right? It would be 99 minus 2 plus 1. Right? This formula is really easy to, not really to prove, just to justify. Very easy. So I'm not going to bother you with that. Right? So later on, when I talk about pattern here, I might sometimes use this notation here, right, for closed interval. It's going to be very handy. Okay, let's come back here. Okay, the number outer loop iteration will be how many? So here, we just get to say from 0 to n minus 1, right? So that one is there is going to be n iterations. All right, so let's highlight that right away. We got n iterations. So I will be from 0 all the way to n minus 1. And let's now talk about the inner loop. Basically, the inner loop is going to be run for every value of I, right? That's the meaning for nested loop. That one I assume you know from the first year. So now for I is equal to 0, what's going to be the value for j? 0 to n minus 1. Similarly, right? You can see here almost the same, just rather than I is j, right? Okay, so here I'm going to put j here. It's like a second dimension. J is going to be from 0, 1, 2, all the way to n minus 1. All right? And here we also know that in the loop, we got n iterations. Right? You can see we go from 0 to n minus 1, just the same interval. All right? And then what about when I is equal to 1? Would it be the same? Yeah, the same. Because you can see every time we want to run the inner loop, we always start j with 0. We don't start with, for example, I. That's something we'll see later. Okay? So when I is equal to 1, it will also be from 0, 1, 2, all the way to n minus 1. And 0, 1, 2, all the way to n minus 1. And continue. What about the last possible value for I? Also the same, right? Just the same. So it'll be 0, 1, 2, all the way to n minus 1. And now, once we have got this pattern very well observed, so this cell over here talks about the combination of I, j as 0, 0. And this one here is about 0, 1. And this one here is about 0, 2. For each combination, we're going to execute this green part, right? How many, right? That's something we got to work out. So it's like a rectangle. What will be the width? N. What will be the length? N. N times n. So we got n squared possible combination of I and j. For each combination, we're going to execute this once. All right? That's a very important insight you want to convince yourself, maybe after the class today. All right? So let me just write down one more insight here, right? For example, this one here, this is the ij combination of 2, 2, where line number 4, right? Line number 4 to line number 6, right? Over here. Line number 4 to line number 6 is executed once. All right. The only thing I didn't talk about yet, which is this guy here. What will be this one here? This one's completely outside the loop. That's constant, right? Let's consider that as well. Let's now try to add up everything together and see what's going to happen. So the running time is going to be the big O. I'm doing intermediate work, so I'm going to do some summation inside just to show to you, right? Let's start with phase number 1. This one here is going to be about how many combinations here? We said n squared, right? You can think about here we got n times n, okay? And then times 1. Okay, let me just annotate a little bit. So n here is about the number of values of I, and the n here is about the number of values of j for each I. And the 1 here is about line number 4 to line number 6, right? About each time. Line number 4 to line number 6, right? So we calculate exactly how will be approximately the number primitive operation here. And what about phase number 2? How should I approximate it? Should I say n squared? N, all right? That one there only depends on the outer loop. All right, so that one there I'm going to say plus n times also 1. So for this one, n over here is the number of values of I, just that. And the 1 here is about line number 7. All right? And finally, I'm going to add this one here as well, right? Just for completeness. That one there would be plus 1. And that one there is line number 8. Okay, let's now add them up together, right? We go off. So here we got n squared plus n plus 1. n squared plus n plus 1. And before we present the final answer, this is the highest power. No multiplicative constant drop, but drop the lower term. So finally, we got big O of n squared. That will be the final answer. So it's a quadratic algorithm. Okay? Not surprising. Our initial guess was completely right. But the thing is, to really get a full credits, we need to show the process, especially how the loop counters are going to change. That's the thing I'm looking for. And we're going to do one more example today where the patterns will be a little bit trickier. Okay, question?
So I know we're not doing exact, but for I plus plus, right? Does it go exactly n times, or is it like n plus 1 or n minus 1?
Yeah, exactly. So here, for I++, we don't really have to worry about whether it's going to be executed n times, n minus 1 times, or n plus 1 time. Because now we're approximating and we're trying to derive the upper bound, so we don't need to. On the other hand, if I ask you to calculate precisely how many times this is going to be executed for the precise number of primitive operations, then you have to worry. Right? Let's worry about that in another context. But for now, we are only approximating. Okay? So I'll be, good. All right, any question? All right, just the first one. Before we do the second one, let's do a little bit of variance over here. I still got contains duplicate here. I just want to clarify maybe some confusion. Does it really mean every time we got nested loop, then the guess should always be n to the power of 2? Not necessarily. All right, I'll show to you. Just an example. All right. I just copied the contains duplicate from the previous page over there, right? It alone is n squared, as we just saw. I'm just going to somehow play with the bounds in the loop over here to give you one example where rather than n squared is going to be n. Another one is going to be not n squared, but just constant. Okay, very easy to play with. Okay. The first one here, I'll just say rather than, let's say for the outer loop, rather than n, I might just say 10,000. Now, what will be the ultimate asymptotic upper bound? Would that still be n squared? Not really, right? Think about this 10,000 here. It's just a multiplicative constant that might just end up being dropped. Okay, and for this one here, you can think about it's going to be big O of how many combinations are there? As you can see, the combinations of I and j is going to dominate. It's going to be the highest term for the algorithm. So we just need to focus on that. Let's say for this variant here. How many combinations will there be for I and j? Briefly. Should be just n multiplied by the number of iteration for the outer loop, right? Which would be about 10,000. Okay? So that one will be about 10,000 multiplied by n. And this can be dropped. It's a multiplicative constant. So it will just be big O of n. So you can see we got nested loop, but it's linear. Simply because one of the loops there, their bound does not depend on n. It depends on just some fixed constant, which will be dropped anyway. Right? And I'm pretty sure you guys would know, how can I modify this guy here to make it constant rather than linear, to make it even cheaper? I can simply change the two bounds to be constant. Right? Because we talk about asymptotic, doesn't matter how large the constant is, doesn't matter. Right? So I can change maybe this one to be 1 million. I can change this one to be also 1 million. I'm exaggerating a little bit, but the point is, asymptotically, simply we can go all the way to the infinity, right? Even that is just going to be big O of 1 million times 1 million. And that one there is just going to end up being some very large constant times n to the power of 0. Right? It would just be big O of 1 still. Right? That's how you should think of it. Right? Anything that's not just going to be depend on the input array size n, it's just a fixed constant, it would just be constant. Right? Doesn't matter how large it is. All right, so that one there is just another one here. So that one is a little bit more expensive. All right, any question about these two? Okay, good. Let's now do maybe one or two more, and then we do some tricky ones. That'll be the trickiest one for today. Okay, let's do that in a moment. All right, so this one is easy. Why don't you guys take a look and tell me what will be your guess, the asymptotic upper bound. I got 3 loops. A possible guess could be, should that be n to the power of 3? No, right? Okay. What should that be?
N squared.
I heard n squared. Anyone else? N squared? Agree? All right. Let's see. Line number 2, constant, right? Just 1. And the first loop here is more like a find max kind of thing. That one there, you can see the number of iteration will just be n. So I'll just put n here. And then line number 6 over here, this will also be just 1. And then line number 7 to line number 9, this will be similar to what we did earlier. Okay, so you can see here we got n here for j, we got n here for k, right? We can follow exactly the same approach. That'll be n squared. And then we got another one, the final line, line number 10, is also constant, right? I'm going to put 1 here. All right, so the answer will be big O of 1 plus n plus 1 plus n squared plus 1, right? So big O of n squared plus 2n plus 3, right? You can drop lower term, n squared. All right. That'll be the final answer, n squared. So it's not really n cubed, even though it is correct to say it's n to the power 3. But we talk about the most accurate, right? We talk about accuracy versus correctness, right? Last time. Any question about this one here? All right. Let's now do this one here. This will be the last example on applying, but we'll see more, way more later throughout the course. This will be the last one for the asymptotic lecture. Again, you don't necessarily have to understand the logic of this piece of code over here. You don't have to if your only goal is to just to derive the tightest asymptotic upper bound. Right? That's our goal right now. So let's not worry about the logic, but if you're interested, feel free to trace it. It might also be beneficial. All right, so let's now do some very similar annotation here, and we're going to do our usual business, right? You're going to look at a loop pattern, counter pattern. Let me just highlight this part here, which will be the nested loop. And we're going to look at that in just one moment. But it is important to say, for example, this line over here is just constant, right? I'm just going to put 1. It's outside the loop. Also, this guy here is also constant. I'm also going to say it's 1, right? And the one I'm going to highlight in line number 5, this one here gets to be executed for every combination of I and j. Agree? It's within the nested loop, right? So this one here is executed for each combination of I and j. So now we're going to figure out how many combinations are there for I and j. Precisely. How about that? That's something we got to see. Once we get a precise number, and we can approximate it. Okay? I can even tell you the approximation is about n squared. I can already tell you. But we're going to show the work, right? And let's now take a look. So what I'm going to do is I still got to divide into 2 dimensions. First dimension will be I, and second dimension will be j. Right? So let's now take a look. Let's now look at the pattern here. So the pattern for I and j. So the pattern of I and j. All right, let's start with the I. For the I value over here, I'm not going to trouble you. It's going to be from 0. So let's say I'm going to use, again, blue for I and also purple for j. I is going to be from 0 all the way to n minus 1, right? Like before. So I'm just going to say I will be from 0, 1, 2, all the way to n minus 1. Typically, you will be able to see the pattern just to try out the first maybe 2 to 3 value for I or j. You can see the pattern. But if you still cannot see them, you may want to try a little bit more, right? It really depends. But this should be good. All right, so now we can now say right away the number of iterations. The number of iterations for the outer loop is going to be from 0 to n minus 1. 0 to n minus 1. How many? It will be, if you use the formula, it's going to be n. Right? This n will be useful for later. Okay? And let's now work out the j. And I even highlighted for you. J is not going to start from 0 anymore, like in the simpler example that we did about 10 minutes ago. It's going to start with I, which means the starting value for j is going to be 0 here, but it's going to start from 1 here. It's going to start from n minus 1 here, right? It's different. So the pattern is going to be a little bit different. So when you show the work, you're going to figure out exactly how to draw a conclusion from this pattern here, which we're going to see. All right, let's go for the very first one. When I is equal to 0, what will be the possible values for j? From what to what? 0 to n minus 1. I like that. Sure. Okay, so for that one there, j is going to be from, let's say, 0, 1, 2, all the way to n minus 1. That one's easy to see. All right? What about the second iteration for the outer loop? When I is incremented to 1, what will be the value for j? From 1 to n minus 1, right? It's going to be from 1 to all the way to n minus 1. All right? Let's do one more. And when in the third iteration, I will be 2, j should be starting from I, so you'll be 2 all the way to n minus 1, right? So it's going to be 2 all the way to n minus 1. All right? And then you will go on. What about the very last iteration for the outer loop? You'll be from n minus 1, just that, right? N minus 1 to n minus 1, just 1. Okay. It will be just n minus 1. You will see some very kind of nice triangular shape over here, right? I'm just going to highlight that just in case you haven't seen that. We're not done yet. We're only halfway. We now very nicely enumerate all the possible values for combination of I and j. But how many combinations are there? That's the thing. We've got to figure it out. If you look at the first row over here, how many combinations are there? From 0 all the way to n minus 1, which will be n. Agree? Okay. So think about this one here. I'm going to write it down here. So this one here will just be from 0 to n minus 1. That one there will give me n. For the second row, it's going to be from 1 all the way to n minus 1. It's going to be from 1 to n minus 1. That's going to give me n minus 1. And the third one is going to be from 2 to n minus 1, which is going to give me n minus 2. Right? It's decreasing, basically, about how many times the block over here is going to be executed. All right? And then all the way to, what about the last one? It's basically going to be from n minus 1 to n minus 1, just 1. Right? So for row number 1, it tells you that line number 5 is going to be executed n times. For row number 1, it tells you line number 5 is going to be executed n minus 1 time. So what we got to do is we got to sum up n minus 1, n minus 2, and 1. That's what we're going to do. All right? Let's highlight it. N here, n minus 1 here, n minus 2 here, and 1 here. So what we got to do is, so the number of times that line number 5 is executed is going to be n plus n minus 1 plus n minus 2 plus all the way to, let me just move that around a little bit, all the way to 1. Guys, do you recognize this kind of a sequence over here? It has a name. Sequence. Geometric? Arithmetic? arithmetic, right? Okay, arithmetic sequence. All right, let's now review that a little bit. That's going to be something also very useful for you that you have to know. Okay. It's something called arithmetic sequence progression. And I also mentioned something called geometric sequence or progression. Let's not worry about geometric sequence just yet, but we'll need that very often when we talk about trees. That'll be a very natural way to really observe the pattern for trees. That's something we'll get to after the reading week. But let's focus on something that's more basic. All right? And very quickly, so there will be some terms you have to know, right? Let me just, what will be the general form for the arithmetic sequence? It will be something called I. I'll just write it down first, and I'll explain to you the terms. And I plus C plus I plus 2 times C plus all the way to I plus n minus 1 times C. That's one way to express an arithmetic sequence. Okay? And we say that the I here is called a start term. And then the C here, well, you can also think about I as I times 0, sorry, let's just say I plus 0 times C. You can think it that way, right? So the C here, just getting incremented, getting accumulated each time. It's called a common difference. So the C here is called a common difference. And finally, it's important to know how many turns there are in this sequence. How many? How many turns are there in this particular sequence? You got to observe the pattern. I already gave you hints by writing this down explicitly.
C times n minus 1 minus.
No, how many turns? Not about the summation. I'm only asking how many turns. Guys, let me state my question again. It's important. We got a sequence of turns. How many turns are there in this sequence? How many? N? Okay, good. Okay, how did you figure? Yeah, go ahead.
Well, you start at 0, in terms of the number next to C.
Yeah,
And that n minus
brilliant. That's exactly what I wanted to hear, right? That's exactly how you should really observe the pattern. You got 0 here, you got 1 here, you got 2 here, all the way to n minus 1. So what will be the interval between 0 and minus 1? N, right? So observing pattern is a very critical technique to have in this course, all right? All right, so now the number of turns will just be 1. That's awesome. So here we got n terms. All right, just about terminology. And what will be the facts? You don't need to prove it, right? You can just use it. So the formula is very straightforward. You basically are going to use the first term plus the last term. In this case, it will be I plus n minus 1 times C, and the whole thing will be times the number of turns, which will be n, divided by 2. Right? So that's the sum. Let me just mention again. It's going to be the beginning term, also the last term, multiplied by the number of turns over here, okay, divided by 2. And this one here, I already calculated for you. You don't need to worry. I just put it down for your reference. If you try to simplify it, it's going to be C times n squared plus 2i minus C times n divided by 2. And what will be the asymptotic upper bound for this? N squared. Okay, thank you. I'm pretty sure that's what you wanted to say, because we can identify highest power, drop the multiplicative constant, drop the lower term. We got n squared. And this is order of big O of n squared. So 2 things you should know. Number 1, you should know that the formula, beginning term plus the end term, and then times the number of turns divided by 2. And it will be normally just n squared. Okay? And let's go back to our original example there and use that. Now we got this one here, right? This is an arithmetic sequence, except that the common difference here is minus 1. Agree? Okay? So this one here, if you try to approximate it, is going to be beginning turn plus the end turn multiplied by how many turns? N turns, right? From n down to 1 divided by 2, right? And this one is big O of n squared. As you can see, n times n squared will be the highest term, right? This will be some mini conclusion we should know, right? N squared. N squared simply tells us how many times the line number 5 is going to be executed for every combination of I and j. All right? Question?
If we know the structure is like triangular like that,
Mm-hmm.
can we not just say it's base times height divided by 2? We know the base is...
Interesting. Yeah, that'll be another way to do it. Yeah, but I think knowing the arithmetic sequence over here, just another way. That might be a little bit more general because you're trying to sum up all the number of iterations. Yeah. So what your fellow student said was also very valuable because this happened to be a triangle. So in that way, you can say what's the length here and what is the length here. This times that divided by 2.
I think you get n squared as well.
Yeah, you definitely get n squared for sure. It's consistent. But I would say what I'm showing to you here is a little bit more general. It's just about counting how many times. And then you kind of observe the pattern from the summation. And then sometimes you may have to use arithmetic sequence. Sometimes you may have to use different progression formula. So you can choose either one. Yeah, but this one is nice. Okay, very good insight. All right, so let's now final answer. So final answer will be big O. And for line number 2, we got just 1. And then plus, and we know the number of combination of I and j will be n squared. Multiplied by line number 5 will be just 1, right? We said that earlier. Okay, so I said something else. I'll put 1 here, right? I forgot to put it. Okay, 1 here. So can think about this will be the number of I and j combination, and this one will be just line number 5. And then plus 1, which will be line number 6, the return. Okay, I think that's what we have, and then that'll be big O of n squared plus 2. And obviously, it will just be n squared. That'll be the final answer. Still to end up being a quadratic, but it is important to really learn how to observe the pattern over here and then work out the answer, right? You don't want to just guess, even though you guess might be right, but it's good to justify. All right, any question here? We're good? All right. All right, so I think that will be the end of the asymptotic analysis lecture. Let me just double check. So we talked about this example already. We talk about this, we talk about this. All right, so this one just repeating the first page, right? Just about you should really know J-unit test, etc., right? And that'll be it. All right, I would suggest I got about 30 minutes. Let me do a little bit of introduction, one example about the next lecture. 10 minutes, and we'll take attendance and then take a short break, and then we'll continue. Okay, we should be able to talk about selection sort versus insertion sort. I think that'll be beneficial. Okay. Let's take it another 10 minutes or so. The lecture slides are already on the lecture site. I make some slide modification today, so just rearranging the order slightly. But I'm going to update that a little bit later today. All right, so for this lecture here, we're actually going to revisit the array that you guys know very well. But we're going to apply what we learned from the previous lecture and see what would be the scenario where array will be expensive to use. Right? That's also important for you to make some informed decision later. And definitely, very, very important topic will be linked list. All right? I may not be able to get to it today, but definitely Thursday. And for your information, recursion and linked list will be the topics for your programming test number 1. All right? So definitely still review recursion, still do more exercises, but linked list is also very important. Okay? I'll speak more about it. Linked list, very interesting idea. We're going to do lots of drawing in the class. That's the only way to learn it. Okay. All right. So we're going to go over. Okay. So basic data structure, arrays versus linked lists. So we're going to see that after this lecture here, whenever you want to implement so-called abstract data type, which I'll talk about later. For example, if you want to implement a stack, you want to implement a tree, you always got at least two choices, either using an array or to use a linked list. But to really decide which one to use, you have to know what kind of operations are involved in your application to decide accordingly. That's something I'll talk about. Right? Very important to clarify. And we're going to talk about selection sort, insertion sort. If you remember on day one, I talked about like 5 different sorting algorithms. So these are 2 of them. Not bad, but when input gets very large, these 2 will get very slow. But it's also important to learn it. And then once we get to linked list, there will be a notion about either singly linked or doubly linked. I'll explain what it means. You don't need to worry now. And also the runtime, we're going to compare about array versus linked list operation. So there will be some tables to really summarize the result. But of course, you don't want to memorize the result. You have to understand really how those things can be derived from the diagram. So just in case you forgot, during the test or the exam, you can still build from scratch. It's not difficult. And we'll see also some Java implementation detail. That's something I'll show to you, right? Because once you get assignment number 2, you will be expected to use something called generic list. I may assume you guys haven't really learned about it in 2030. I'll see how much I can really cover in the class, but there will be some explicit instruction in the assignment anyway. But we'll get there. Okay. For now, you don't need to worry. I'll give you more guidance later. All right, let's now talk about arrays. Just a very quick summary, and I'll go for one example. And then we'll take a short break. All right. All right, so array sequence of index element. So indexing is basically where all the operations are going to occur on the array, right? Indexing, right? Calculating the address. All right, so let's go over some basic facts. The size of an array is always fixed when you actually try to create it. What this tells you is, whenever your application have filled out the array that you have initially created, if you have the need to create a larger array and copy over the contents, that would be an expensive operation. If your application requires such constant growth of your array, you shouldn't really choose array. You should choose maybe linked list instead, for example, right? That's kind of the story you want to think in your head. However, I want to give you guys a heads up over here, right? This will be something either I can guide you through very briefly in the lecture, or I do have some nice pre-recorded lecture to talk about this. So people do choose array as a data structure. However, the way they grow the size of the array is not to say every time I want one extra space. So I just grow the array by size plus 1. If I need 2 spaces, I will say size plus 2. Not that. That will be too frequent. So what they will do instead will be some resizing strategy. One is called increments, the other one is called doubling. Okay, anyway, just the terms I want to mention. I might be able to give you a little bit more detail later. But in order to work out the running time for these 2, we will need to do something called average case analysis. If you remember what I said earlier, we're going to focus more on the worst case. But these 2 strategies, to really see their benefits from one versus the other, you will need some average case analysis. Some heavy math will be involved. But we'll see. All right, so what will be the operation for the array? Let's talk about some basic ones. If you just want to access into an array, constant, right? That one just a primitive operation. If you want to maybe write something to the array, similar, also constant. Also indexing, just change whatever that's in the index. However, the third category here is going to be the expensive category you want to avoid as much as you can for array. Whenever you say, I want to insert something into the array, or I want to remove something out of the array, that potentially can be expensive, potentially. Okay? So let's go over one example here before we take a short break. So this is a block of code I'm going to go over with you, and then we're going to work out maybe a little bit about how it works. I'll show you some visual, and then we're going to derive the asymptotic upper bound from there. You can see so far the operations we have for array are simply just constant. But for insert and remove, we're going to see that it is strictly more expensive than indexing and also updating. All right, let's now switch to this one here. All right, why don't you guys take a look at this code here just for one moment, okay? And then we're going to work out exactly how that works. Yeah, I'm going to trace together with you just to see how it works. But before that, can you guys somehow take a guess? Based on the example we went over, this one should be quite easy to derive, right? Somehow. What's the asymptotic upper bound? Big O of n? That sounds like a linear, right? Okay. That's a good guess, but we're going to see exactly how, right? We're going to see. Very good. Good guess. Good guess. Okay. All right, so let's now, first of all, just before I go over line by line with you to derive the upper bound, let's now take a look at how the algorithm is supposed to be used, the method. The method is going to, it's called insert at. It's going to take one array and return a new array. And in addition to the input array, we're also going to pass the size of the input just to a little bit easier for us to do analysis, right? N here will just be a.length, you can assume. So the n here would just be a.length over here. And also this string here will be some new elements we want to insert into the array. And also I here will be where exactly to insert into the array. Okay. So here this will be, this one tells us we want to insert E, the new elements, to index I. And I here we assume can be any value from 0 all the way to n. When it is equal to 0, that means the new element is supposed to insert as the first one in the new array. When it is equal to n, it's going to be at the end of the array, right? Something like that. Once I do some tracing for some example, you can work out exactly how it's going to work, okay? All right, let's now go over some example before we look at the code. Actually, we should look at the code at the same time. Okay. So let's say here I got insert at, I got input array, I got Alan, Mark, and Tom, right? So here I got Alan, I got Mark, and also I got Tom over here. And this is the input array, A. And I say I want to insert, so the 3 here is simply the array size, just 3. Okay. I say I want to insert a new string called Jim into index 0. All right. And let's see exactly how it's going to work. Well, obviously, when it is equal to 0, that means 0 index, the first one there, should really store Jim afterwards, right? Let's put Jim down. Okay. But also very important for you to see, the resulting array is exactly 1 larger than the input array because we need to insert exactly 1 element, right? So now you can see that Jin is going to be inserted right here. You can think about the Jim here is corresponding to the element that we want to insert. And also you can think about the 0 over here is the I here, right? We want to insert right into I. Right? And now the tricky bit is here. Given that Jim has been inserted, but what about the rest of the new array? We have to somehow copy over the old array into the new array. So Alan should really go to here. Mark should really go to here. And Tom should really go to here. Conceptually, it's easy. But implementation-wise, you got to watch out for the indices, right? So you can think about what's going to happen is, so 0 here should be copied over to 1. 1 here should be copied over to 2. And 2 here should be copied over to 3. Right? So that's how we're going to get Alan, Mark, and Tom. And to be more precise, when we do the copy here, you can see starting from, let me just write some pattern here for you so you can observe for later. Okay? So here you can see the result. Index 1, which is over here, is just the same as the input array at 1 minus 0. And also result at index 2 is exactly equal to 2 minus 1. And also result at index 3 is equal to A and then 3 minus 1, right? So the minus 1. So I beg your pardon, this one is definitely not the case. Should be 1 minus 1. So the minus 1 here is really the key, right? Minus 1 here, minus 1 here, minus 1 here. So that's exactly what you will see in this particular iteration here, right? That's what you will see. All right. In order to assign this, you should go to the location that's 1 less in the input array. Okay. Let's now go over very quickly the code structure and then work out the asymptotic upper bounds. Okay. And I'm going to use another example. So that one, this one here, somehow I'll put down here. That's something you can also observe for later. This one over here is the worst case for the second for loop. And the second for loop I'm talking about is exactly here, the second for loop. It is the worst case in the sense that you have to copy the entire input array into the new array. There's nothing else before that you have to copy. You will see, right? When I see the second tracing. All right, let's now go over the code structure here, the logic, and then we'll use this example just once more. Okay. So look at line number 1, this line here. We're just creating a result with one more element, right? You can see n plus 1. There's something I didn't really include in the original list, but whenever you're trying to create a new object, it will just be constant operation, right? So you can say object creation is a constant time operation, right? So this one here, I'm just going to say 1. It's a cheap operation. All right, just for this one here. Okay, I'm just going to put 1 here. All right. And then the first for loop here, what does it say? It says that I'm actually going to do some copy here. I want to copy from the input array A into the result. And what we're doing here is, for example, let's say I got Alan, Mark, and Tom, right? I got Alan, I got Mark, and I got Tom, right? You can see, again, 3 here is just the size of the array. So you want to focus on this value over here, right? That's 1. I want to insert Jim into index 1. Index 1 is here. Okay? Index 1 here, which correspond to the index 1 over here. So what does that mean? That means I may insert Jim to be here, but who should come before Jim? It should be whoever that comes before index 1. Right? That's insert at. Exactly, right? So that's exactly what the first for loop is going to do. It's actually going to say, I want to have some loop counter from 0 all the way to I minus 1. You can think about this element here is I minus 1. So think about this one here is I minus 1. And this one here is I. I want to insert Jim into 1 here. So that means everyone before index 1, in this case just Alan, they should go to here. And in general, it could be more than 1 element that comes before I. So that's why you need to use a loop to really handle that, right? All right. So the first for loop, I'm just going to use green, the first one. Okay, the first one. The first one here is just going to copy everything that's to the left of I. In this case, just Alan. So I will put Alan just in this index. You can see result J and AJ. So that means result 0 is going to be assigned to A0, right? Straightforward. So that's step number 1. Let's work out the running time right away. What will be the running time for this? This one should be rather easy, right? What would that be? If you somehow want to look at what will be the number of iterations, right? So let's see J here is going to be the interval of from 0 all the way to I minus 1. Agree? So that means there will be I iterations. And what will be the value of I? Our assumption is I can go all the way up to and including n. So that means the running time for this one should still be n. I iterations, that means n times. For every iteration, we're just going to do some array updates, array indexing, and also assignments, which will be just 1. Agree? Okay. So you can see just this array assignments alone is going to be just 1. But overall, I'll put a star here. Okay, for star, I'll put a star here. It's going to be big O of how many iterations? N iterations, because the maximum value for I can just be n. So that'll be n times 1. So think about the n over here is the max value of I. And the 1 here is simply just a copy here, right? Just a copy here. Okay. So that means for the first for loop, I can just put n here. All right. So it's very important for you to see, once you figure out it should be I iterations, but I here may not lead you very far. You want to know what's the bounds on I. So that's why I figure out it's n, given the assumption I mentioned to you. All right, so next line. And I'm going to assign the new element E, in this case Jim, to index I. All right, so assign Jim into index 1. So I'm going to do that. So it's just going to be Jim over here, right? That's a I index. Finally, okay, so this one here is just going to be 1. Okay, a few minutes, and then I'll finish this, and then we can take a short break. All right, and the next one here will be like here. This blue one over here. All right. So this one here is going to be, we're going to start with I plus 1. So think about this will be I plus 1. We're going to start with this. So this will be the I plus 1 index. Start with this. And what should be copied over to index 2? It should be mark, which will be at index 1. We talk about like a one-off difference, right, for the indices. That's something we talk about in this example here. Right? We're going to copy to here, index 1. We're going to copy to here, index 2, and etc. All right? So that loop there is actually going to copy Mark over to here and Tom over to here. So Mark and Tom. And so that will be the resulting array. So that's a tracing. But what will be the running time for this? Just line number, well, just this second for loop. And yeah, that's true. But let's also work out the exact details, right? Thank you. I agree. But let's now take a look. If you look at the loop counter over here, so the j value is going to be from I plus 1 all the way to n, right? According to our little formula, the number of iterations is going to be n minus I minus 1 plus 1, right? It's just going to be n minus I. All right? N minus I, and I indeed is just a constant. Well, think about what will be the minimum case for I. The minimum case for I would just be 0, in which case n minus 0 will just be n. So worst case will still be n, right? So this will be also n times. All right, so let's now do this one here. This will be just n. All right. We got n iterations, and for each iteration, we just got constant operation here. All right, finally, we got return, which will be just constant. And for this one here, let me say constant here, and then we're going to add up everything together. So it's going to be big O of 1 and 1 and 1. 1 and 1 and 1. And you can see the highest term will just be n. And drop all the lower term, multiplicative constant, it will just be big O of n. So this example here, the reason that I really want to dive very deep into details, several reasons. Number one, well, just like a nice exercise for us to see the loop pattern again, a simpler one. Number two, this one really shows to you every time you will actually need to do any array operation that's going to involve copying contents over to another array, most likely it's going to be an expensive one. So you got to watch out for that. And also tracing is important. You want to work out what would be the correct logic for, maybe for example, what would be n minus 1, j minus 1 here, right? That's another reason. Right, anyway, exercise for you. Try to see if you can trace this particular call here, right? Exercise for you. All right, any question? Question here before we take a break.
Question with J. J runs from I plus 1 to n, so how is it
n minus I? Okay, sure. I'm glad you asked. Let's try. When I got I plus 1 to n, right? According to our formula, it's going to be n minus I plus 1 and plus 1, right? It's going to be the beginning of the n minus the beginning plus 1. That's the formula, right? So now n minus I, and then I got minus 1 plus 1 cancel out. So n minus I. No problem. I'm pretty sure other people got the same question. All right, guys, why don't we take a very short break by taking attendance, and we can talk a little bit about sorting maybe after the break. All right, so we should really get to the next one, which is about comparing two sorting strategies, namely selection sort, insertion sort. I cannot really get to these two today. Only got 5 minutes, but I would say we clarify some terminology very quickly in 5 minutes. I think that would be beneficial as well. It's going to be covered anyway. So we talk about computational problem. Input is just an array of number or sequence of number. And here you will see this very often like a non-descending, right? So now I want to clarify this, a little bit more, just in depth. Whenever you're talking about sorting, so they don't necessarily always say it's going to be non-descending. They might say in different ways. They might say non-descending, yes. They might say ascending, increasing. They might say non-ascending. They might say descending and decreasing. Things like that, right? So given each one of these, your implementation may have to be adjusted accordingly. So now I want to clarify what these four really mean. And by drawing some visual, and if we got enough time, I only got 4 minutes, but maybe we'll do some little exercise to check your understanding next time. But at least let me clarify. And then we'll talk about insertion sort, selection sort for sure on Thursday. So now we basically got 4 possibilities here. We got decreasing, increasing, we got non-descending, we got non-ascending, right? Very easy to understand. Let me just visualize them. So let's talk about the easiest one, decreasing or descending. One example would be, let's say I got 5, 4, 3, 2, 1. This would mean whenever I choose any adjacent elements over here, it should be that if it is decreasing, that means this element here must be strictly larger than this element here. It must be strictly larger than. All right? And visually speaking, your array value from the left to the right should be something like this. Like it should be like a downward trend. This would be, for example, A, maybe I. This will be A, I plus 1, right? They are adjacent. Right? You can think about this is like AI. This is like A, I plus 1. And 4 is strictly larger than 3, right? That's about decreasing, descending. Easy. Symmetrically, when we talk about increasing, ascending, just the other way, right? One example would be, let's say 1, 2, 3, 4, 5. And if I choose any 2 elements over here, now the relationship should be smaller than because it's going upwards, right? So the trend should be something like this. This will be AI, and this will be AI plus 1, right? You can see strictly smaller, right? And one very important observation to make. If you actually got either decreasing or increasing, that would mean your input array or output array should not contain any duplicates. Okay? Duplicate what might mean if I got 4 and 4, then strictly larger than is not going to hold anymore, right? So duplicate is not good, okay? So here we just say no duplicates. All right, so now, before I visualize these two, I only got 1 minute. I don't want to drag you later than I should. I'm just going to work out the logic very quickly for one of them, and then we'll continue from there. What does it really mean when we say non-descending? Okay, only this one. Take about 1 minute. When I say non-descending, by definition, the none here is like a logical negation. That means it is not the case that we are descending, obviously. And we talked about descending already. It's about this element here strictly larger than that. That means it is not the case that AI is strictly larger than AI plus 1, right? We're saying that it is not the case, not descending. So you guys learned about De Morgan. Well, actually, not even De Morgan, just about, sorry, not De Morgan, I beg your pardon, not even De Morgan. You're just negating larger than, which will be smaller than or equal to, right? Yeah, forget about De Morgan. I really didn't mean to say that, okay? Equivalent to AI less than or equal to AI plus 1. All right, so we are basically turning from larger than into less than or equal to. So that less than or equal to is really what non-descending means. All right, so think about this kind of derivation over here. We'll spend just about a few minutes on Thursday to finish this and do one exercise, and we'll continue with the insertion sort, selection sort. Thank you.